Thank you all for coming. It's my great pleasure today to introduce Dr. Vanessa Huxter as our colloquium speaker. She has recently joined the faculty here at the U of A. In August of 2013, she became an assistant professor in the Department of Chemistry and Biochemistry. She received her Bachelor's of Science degree from McGill University and her PhD from the University of Toronto, and went on to hold a prestigious NSCRC postdoctoral fellowship jointly at UC Berkeley and Lawrence Berkeley National Labs. She's authored a number of papers and book chapters on topics ranging from semiconductor spin dynamics to correlation of molecules and vibrational coherences in solid-state materials. And today she's going to tell us something about her more recent interests. Vanessa.
Thank you very much. So, diamond defects in plants, two pretty disparate systems. They're linked by the fact that we really don't understand much about their ultrafast dynamics. We really don't understand much about the way that energy moves through these systems in real time. When I'm talking about plants, specifically what I mean is the light harvesting antenna of photosynthetic systems. And surprisingly, despite many years of research on these systems, we really still don't understand what's going on in photosynthesis. In fact, only a couple of years ago, using some of the techniques I'll be talking about today, there was a major discovery made that showed that plants are using, or suggested that plants are using, some sort of quantum coherence in order to maximize their energy transfer rate. So in terms of diamond defects, well, diamonds have been of interest for a long time. Some might say forever, even though they're metastable and slowly turning into graphite. Diamonds have a number of interesting material and physical and optical properties, not the least of which is hardness. And actually, the material hardness of these systems means that it can of diamonds means that it can accommodate a large number of different kinds of defects. So for instance, this is where we get color centers from. If you replace some of the carbon atoms in the lattice with boron, you get blue diamonds. If you replace some of the carbon atoms in the lattice with nitrogen, you get these beautiful yellow or canary diamonds. There's actually a wide range of different kind of nitrogen defects that you can have in diamond. And the one that I'm going to be talking about today is something called a nitrogen vacancy defect. In a nitrogen vacancy defect, what you have is you have a nitrogen replacing a carbon in the lattice, nearest neighbor to a gap, basically a missing carbon atom. That's what's called the vacancy. And just to be clear, there are a number of even different kinds of nitrogen vacancy, but the type that I'm going to be talking about today is a negatively charged nitrogen vacancy. So you actually create these diamonds, you grow them, you then irradiate and anneal them, and you localize electrons onto these defects. They have a fairly interesting electronic structure. Their ground state is a triplet state, so ground to excited state is a triplet state. This transition is in the red. It's at about 640 nanometers. There are also singlet states which are in the near IR. And if you'll notice, I've kind of hinted at here, there's a fairly significant vibrational or phonon sideband sitting on top of these levels. It's actually enormous, as I'll show you later. There's been a huge explosion in research on nitrogen vacancies in diamond. It's kind of the darling of physics right now. And one of the reasons for that is because it has a number of really attractive properties that people want to use in order to build new kinds of devices. Most of these devices actually focus on these spin states here that are associated with the ground state. But you can address these spin states optically and magnetically. And what I mean by optically is you can actually pump from the ground to the excited state, take advantage of this intersystem crossing pathway to address your spin states in the ground states, simply by pumping it with green light. So some of these applications are what's called sub-diffraction limit imaging. We're not actually beating the diffraction limit of light, but there are tricks that you can play to effectively be able to image at the sub-diffraction limit. And that has to do with the fact that these never photobleach, ever. You can hit them with a huge amount of light. They're just going to continue to emit. Also as single photon sources, so you can actually go in and implant these in arrays, and they actually work fairly well as single photon sources. Another one of the major applications for these things is basically as a qubit. They have spin coherences that last for seconds at room temperature. That's really exceptionally long for quantum mechanical type behavior. You actually couple to the carbon-13 here to get that. While that's not at the place you'd need it to be in terms of lifetime for the spin coherence to actually build a quantum computer, it's getting to where you need to be in order to build something realistic. Perhaps, well, at least the application that I'm the most interested in is this idea of being able to do magnetometry on the nanoscale. And basically what that means is being able to do NMR or something equivalent not only on a single residue in a protein, for instance, but on individual atoms. And actually the Pines group in Berkeley is at the forefront of this work. So lots of different interesting applications. However, this defect does not exist in a vacuum. This defect is sitting in a lattice. It's coupled to a large number of vibrations. And actually, before the work that I'm going to show you, people really didn't have any idea about what was going on in terms of the vibrational bath of this system, so the vibrations all around the defect. So that's one of the things that we wanted to learn about. What's actually going on with these vibrations? How is it interacting with the defect? This will affect, basically, this will influence all of the different properties, the exciting properties of this system that people have been trying to exploit to build these new devices. In addition to the vibrational bath and how it interacts with the defect in terms of decoherence effects, etc., we're also interested in finding out how fast relaxation is through the excited state here. So as I was saying, when you optically address these things, you excite from the ground to the excited state, and you actually pump beyond the band gap and wait for it to relax back down before it goes through this intersystem crossing pathway. And the time scale of relaxation through this sideband is actually really important for understanding some of those processes. Okay. So there are a number of major questions we had about this system before we started looking at it. Basically, nothing was known about the ultrafast dynamics of the system at all. The fastest time scale was nanoseconds, and that's for the fluorescence decay of the system. When I say the definition of ultrafast is always shifting. So now we have attosecond, et cetera. And when I say ultrafast, basically what I mean is femtosecond and picosecond, which I'll come back to. We didn't know which modes were most strongly coupled to the defect. We didn't really understand how they affected the system. Didn't know whether or not they were local to the defect or delocalized through the entire crystal lattice. And we also wanted to understand or know about what the time scale of relaxation in the phonon sideband was. Okay. So how are we actually going to be able to measure this? Well, we can actually take inspiration from some recent work that's been done on photosynthetic systems using a technique called two-dimensional electronic spectroscopy. So this technique has actually been used very successfully to follow what happens after light is absorbed in a photosynthetic system. This is the antenna here. So light is absorbed as a photon. You then transfer the energy through the antenna and eventually to the reaction center, which is where you actually begin to store the light energy as chemical energy. So we're going to use a similar method to be able to look at what's happening in terms of the ultrafast dynamics of energy flow in the diamond defect system. So one of the obvious questions might be, okay, this seems like a pretty complicated technique. I've already said it's a 2D electronic spectroscopy technique. I've said it's ultrafast. Specifically, it's a third-order nonlinear optical technique. And the question would be, okay, well, why would you need to go that complicated? And the answer is basically because you don't have any choice. If you could do, let's say, if you have to do an ultrafast technique because we're interested in things that are happening on the time scale of femtoseconds and picoseconds. So those are the time scales of vibrations. Those are the time scales of energy transfer, et cetera. So we need the proper time resolution to be able to observe those dynamics. It's similar to the idea used by Edward Maybridge when he developed a new camera system to see whether or not a horse picked all of its legs off the ground when it was at a full gallop. Why do we want to do a nonlinear measurement? If we could do a linear measurement, like absorption or fluorescence, we would absolutely do that, no question about it. However, when you do a nonlinear measurement, you can access different kinds of signals. You can also isolate different components to your signals based on scattering rules. So basically, we have to do a nonlinear measurement because the kind of information we're interested in will be in those measurements. So you might say, okay, well, why do a 2D measurement? There's lots of perfectly good one-dimensional nonlinear optical experiments. So for instance, pump probe, right? In a pump probe experiment, you have a pulse comes in, it pumps your population, so you basically excite the sample, you move population from the ground to the excited state, then you come in at some later time with your probe, you watch it relax back down. That also gives you a lot of information. That is also a nonlinear ultrafast technique. However, you lose a lot of information. Basically what happens when you do a pump probe experiment is it's as if you're integrating over this axis here. And that's if you're doing a frequency-resolved pump probe experiment. If you're doing a single color, you integrate over both axes. So if you have off-diagonal features like this, if these two peaks were about the same intensity, you might lose that peak altogether. If you'll permit me a little bit of a silly example, let's imagine that you're lost in the Celestial Mountains in China, and you want to get from point A to point B. Well, if you have a 2D map, it's really easy to see that you just follow this ice flow here. You very easily get from point A to point B. However, if we were to integrate over this axis here, you'd know you're in the mountains, but you'd be completely lost. So, yeah, there's lots of times when doing a pump probe measurement is all you need to do. If you're interested in just population dynamics, pump probe measurement is great. Here we're actually interested in both populations and coherences. So by that I mean both the diagonal and the off-diagonal components of the density matrix. And so you really need to do a 2D measurement in order to be able to see where the energy is going. Okay, so how do we actually do this experiment? So in our third order experiment, it's third order, so we have interaction with 3 beams, 3 ultrafast pulses there. We focus our 3 beams into the sample, and the signal is scattered in this phase-matched direction based on the geometry of our incoming beams. We mix it with a reference frequency, so very attenuated, called a local oscillator. That name is a little bit of a holdover from radio measurements, but it's still called a local oscillator. Basically, it's just a reference signal that allows us to collect a heterodyne, allows us to heterodyne our measurements so that we can separate out our real and imaginary components, our absorptive and refractive components, and it actually gives us a huge signal-to-noise advantage. We collect our signal in a spectrometer. The spectrometer does the first Fourier transform, and we collect our data on a CCD as a frequency-dispersed signal. So when we're doing the experiment, we start at the ground state. First pulse comes in, and it drives a coherence between the ground and the excited state. So we're actually in both of these states simultaneously. So you're accessing the quantum mechanical information there. Second pulse comes in, and it puts you into a population either in the excited or in the ground. I haven't drawn that because otherwise it's just 2 bars across. It gets very confusing. But you're evolving through a population in either the ground or the excited state. Third pulse comes in. This third pulse is a complex conjugate to the first. And put the system back into a coherence, and the signal is emitted as a photon echo, which is similar. If people have seen spin echoes before, there's an analogy there. Okay? So basically what happens, 3 pulses, signal is emitted, you're accessing both your coherences and your populations. So when we're actually doing this measurement, each one of these 2D plots that you'll see is basically a snapshot along our excited state lifetime. So each one of these 2D plots here corresponds to a different point along this time delay here. And what you're actually creating is a correlation map of your nonlinear absorption, so this time delay here, with your nonlinear emission, so your signal over here. So you're able to see where the signal is going, where the energy is going in and where it's coming out at each point along your excited state lifetime. So how we actually do this is, as I was saying, first pulse, we then scan the time delay between pulse 1 and 2. For each one of the time steps between 1 and 2, we create an interferogram. We stack these up together. We Fourier transform over our scanned axis and generate our 2D correlation map. So we get a lot of information of this from this signal. And in fact, I often think of this measurement, even though it can be quite time-consuming, as being the mother of all third-order measurements, because you can actually get a lot of the by integrating over different axes or by looking at the system in different ways, so looking at the raw data in different ways, you can actually recover almost all of the different third-order spectroscopies from this measurement alone. Okay. So why would you? So believe it or not, this measurement, this powerful measurement, was initially envisioned as a way to look at broadening, which might not seem that exciting, but actually if you're talking about things in the solid state or in solution phase, broadening is really very interesting. So let's imagine that you had model 2-level system, magical 2-level system where it's just 2 levels, the energy gap isn't changing at all, maybe it's in the gas phase, and we're doing a 2D measurement on it. Wouldn't be very exciting, because basically our absorption energy and our emission energy would be exactly the same. So when we looked at it at time 0, so at our first point along our excited state lifetime, what we would get is basically an infinitesimally narrow point at omega A. Okay? because you're absorbing and emitting at exactly the same spot. So let's imagine a real system for a moment. Let's imagine that we have a model two-level system, like a dye system, in solution. So we have all these molecules. They're in solution at time 0, so right when you're starting the clock. They might have different conformations. It's dilute, so they're not really talking to each other, but they're talking to the solvent. There's different electrostatic interactions, etc. When you do that, what you would expect to see when you do a 2D measurement is a diagonal elongation. And this arises from basically you're absorbing and emitting the same energy for each individual molecule here, but they're all in slightly different energy conformations. So you have slightly different energy gaps. So when you actually do this is a real measurement here on a dye system. Indeed, you do get something which is broadened along the diagonal. So if you let that evolve in time, so this is room temperature. You're in the solution phase. The solvent molecules are moving around. The dye molecules are moving around. You lose memory of where you were initially. And so when you do that, you basically relax down to something which looks circular here, and you're actually that's just a measure of the space that you're sampling. So you no longer have the diagonal elongation because you've lost memory of your initial position, and it's just an averaging of the phase space that you're sampling with your molecules there. So when we do this on a dye, we indeed, after only 200 femtoseconds at room temperature, see something collapse back down to a pretty circular feature. So we're not only interested in this measurement for understanding broadening, obviously. Let's imagine now that we had a system that had 2 levels in it. We're exciting both of these levels with the laser. So we're driving both omega A and omega B. So we're exciting both of these initially. And so this plot here would be as if you're right at time 0. You're taking that first plot. You're just seeing where you're absorbing and emitting. Nothing's had really a chance to happen. So you're absorbing and emitting at the same energy. And then let's say after some time, so you're basically taking you're looking at a 2D plot which is further along your excited state lifetime. Let's say there's been an energy transfer from this state here down to this state here. That'll show up as an off-diagonal peak, okay? Because basically what's happening is this peak here arises from energy being absorbed initially here and then emitted down here. So you can see where the energy went in and where the energy came out. You can actually get peaks both above and below the diagonal, and that's not a violation of conservation of energy, because you have vibrations, and you're seeing them at different points. You're basically catching them at different points along their motion. So not just energy transfer. From this, you can see both energy transfer and vibrations. And the other thing is these off-diagonal peaks are generally associated with your quantum effects, with your coherent effects. So there's actually, this is just here to show you that there's actually a huge variety of different kinds of signals that you can get from 2D. This is, in fact, an oversimplification. There's even more that you can get when these things overlap, et cetera. But you can get a huge amount of information from this measurement. OK, so let's come back to diamond now. So again, this is just to remind you of the energy level structure in the system. And this is a linear absorption here of our diamond system. You can see that it is massively vibrationally broadened. So there's a couple things to point out here. This little peak here is something called a zero phonon line. And what that means is that in a linear spectroscopy, that's a transition from your ground to your excited state without the participation of phonons, without the participation of vibrations. And if people are familiar with molecular crystals, let me tell you that this plot here was taken at room temperature. It's pretty amazing to see a zero phonon line at room temperature. You see it in diamond, because diamond is kind of a special system because it's so hard, in fact. You'll also note that there's this huge broad feature here. That is the vibrational broadening. That is the phonon sideband. It's absolutely enormous. If we compare it to a pretty vibrationally broadened dye, so this is a laser dye called rhodaman 6G, you can see that it's absolutely dwarfed by this phonon sideband. If we compare it to Thai sapphire, famously broadened, the broadening in nitrogen vacancy diamond at room temperature is actually larger than that of Thai sapphire. So it's a huge effect. So before we did these measurements, all that was really known about the vibrational structure here, there's been a lot of theoretical work, but and there's been experimental work as well, but mostly just based on fluorescence relaxation, et cetera. It was known that these two features here were likely associated with vibronic states, so the electronic transition coupled to the vibration. So this I'll refer to as the first vibronic and the second vibronic state. If you look at the second derivative of this plot, so you can pick out them a little bit more clearly, you can see the features here as well. So this is 0, phonon line, first vibronic, second vibronic. So just to reiterate, this phonon sideband here spans more than 300 MeV, which is more than 10 times kT at room temperature. So the vibrations are definitely important. Okay, so let's look at some initial data here. So again, here we have our absorption spectrum overlaid with the laser spectrum. This laser spectrum here actually corresponds to a time bandwidth product limited pulse of around 15 femtoseconds, which tells you how broad this peak actually is. The spectral bandwidth of this is about 70 nanometers. So when you do this measurement, we get plots that generally have this sort of squarish shape. And actually, something to keep in mind as you're looking at all these plots is the excited state lifetime of the system is around 13 nanoseconds. So all of the dynamics that we're looking at are sitting on top of a relaxation background. So this squarish shape arises basically from the very strong vibrational broadening. So remember how I told you can get above and below the diagonal from the vibrational modes. And that's basically what you're seeing here. So these lines here are to guide the eye. This line here corresponds to the dotted line here corresponds to the 0 phonon line. So this is at the energy of the 0 phonon line. Let me just stress that in a nonlinear measurement, seeing signal at the energy of the 0 phonon line doesn't mean that there is no participation of phonons. What that means is that you're looking at the band edge. In a linear measurement, the 0 phonon line means no contribution from vibrational modes. So this is the emission at the band edge, basically, if you cut a slice through the plot like this. The peak here basically is associated with the peak of our laser spectrum. So when you're looking at these plots as well, you have to consider the convolution between the absorption spectrum and our laser spectrum. Okay, because that's where our signal will come from. And so, like I was saying, if you take a slice here at our emission, basically, if you frequency resolve the emission, you can actually see, again, this is a slice taken from there, and you can see that you can still see the three features as observed in the absorption spectrum. Okay, so what I'm showing you here is a series of these different 2D plots, and the time delay that they're taken at is shown in white here. So this is 40 femtoseconds, 80 femtoseconds, 130 femtoseconds, 2 picoseconds, and 100 picoseconds. 100 picoseconds was the maximum that we went to, basically. So when you're looking at this plot, there's a lot of information here. So to try to simplify this a little bit, I've cut out a small section of the plot here. Basically, this is at the energy of the first vibronic transition. So you're absorbing at the energy of the first vibronic transition, and you're emitting at the band edge, or at the 0 phonon line. Okay, so that's why you have the off-diagonal peak below the diagonal. So if we look at this section, and we integrate over this, if we integrate over this axis here, our omega-1 axis, we can plot relative to our omega-3 axis. That's our emission axis. You can see that even in that little tiny box there, there's a lot of dynamics going on. There's a lot of motion going on. If we integrate over this again to make it clear, even clearer, you can see that there are multiple vibrational modes in there. There's a lot of stuff going on. So basically, what's happening here is we have, and I'll show you some more information on this, but we have coherent vibrational motion, which is lasting for 2 picoseconds, which is actually pretty long for a quantum mechanical effect at room temperature. So what we're seeing here is basically the oscillation of these vibrations superimposed on our sort of squarish background of our nanosecond decay. So we wanted to know more about some of the vibrations that were happening in the system. And as I was showing you before, we can pick out all different areas based on the fact that we have this as a two-dimensional plot. If you were to take the whole thing and just basically process the entire plot, you get a lot of stuff which overlaps. It becomes very complicated to do that. So what we did is we actually we tried to simplify things initially by looking at our emission band. So we basically took a slice and cut out our emission band. So what we've done is we've frequency resolved our emission here based on our absorption axis. Take this out for each one of our two-dimensional plots and plot them relative to our what's called our waiting time or our population time. So this is the time along our excited state lifetime. When you do that, you can see that there are even low-frequency modes coming out here. That's not really surprising. They're probably associated with acoustic phonon modes, sound waves, basically. Let's zoom in. Let's look at the first 300 femtoseconds. So this is similar to the plot that I showed you before, but over the entire region here. And these lines, again, are to guide the eye. This is at the energy of the zero phonon line. This is at the energy of the first vibronic. This is the second vibronic transition here. And you can see that there is a lot of action going on. There's a lot of vibrations that are interacting with the defect. There's frequency wandering. There's other signatures of coherence here. There's a lot of information here. You can see that just by looking at slices that are taken along this point here. So both changes in amplitude, variations in frequency. So when we actually look at a Fourier transform of this to be able to try to pick out some of our vibrational components, this looks kind of complicated, as does this, but we saw the same thing over and over and over and over again. This measurement was done completely separately more than 7 times, and you basically got rock steady Fourier transforms and plots like this over and over and over again. And so just to make sure that we're not crazy here, I want to point out that we're seeing frequencies here that we expect to see. So these 3 frequencies are associated with the energy gap between the zero phonon line and the first vibronic and the second, and between the zero phonon line and the second vibronic transition. So that's as expected. So what we were able to observe was a series of strongly coupled local vibrational modes. And we were actually able to see these modes that were local to the defect. So that means within a couple of unit cells of the defect itself. We were able to see a Raman mode, so that's delocalized throughout the crystal associated with the diamond lattice. But other than that, pretty much everything was local. And actually, when we went and we compared with theoretical calculations, of which luckily there are a lot, we were able to get pretty amazing matches here. And these are calculated in the same way, basically. So when we did that as well, what we were able to see, we weren't able, I'll point out that we weren't able to say this directly, but we were able to match very closely with theoretical values that showed a symmetry lowering effect of the defect. It gets a little tricky to talk about symmetry in these things, but that symmetry lowering, so frequencies associated with that symmetry lowered configuration are likely associated with what, these are the 2 modes in question here, so this mode and this mode, are likely associated with what's called a dynamic Jahn-Teller distortion. So in that case, you have a doubly degenerate excited state coupling to a doubly degenerate vibrational state, and you actually have periodic raising and lowering of the symmetry of the defect. And that's important actually for understanding how that intersystem crossing process works. But even though we weren't able to so we can say that the modes are local to the defect based on our measurement. And we can say that we were able to observe this whole range of modes that are strongly coupled to the defect that are local, and that 2 of the modes that we observed closely match with what has been predicted in theory to be associated with a dynamic Jahn-Teller distortion. So this is a piece of evidence towards showing that. It's not terribly surprising that you'd see that in the system, even though we haven't been really able to directly observe that before, because this distortion is predicted to only have an energy barrier of about 80 wave numbers. So at room temperature, that's pretty insignificant. Okay, so this looks pretty good. We were able to match our results, our experimental results, with theory. But we wanted to take that another step further. What I actually did is I did a really very, very simple simulation. So this is just a simulation where I took a 2-level system. Nothing fancy about it, just a 2 electronic level system. And what I did is I put the experimentally measured modes with their Wang-Riesz factors, etc., into the spectral density here, which is just the Fourier transform of the correlation function. So that's the only thing I modified about the system. There is a Drew de Lorentz here just to correspond for those acoustic modes that you could see coming out at lower frequencies, so at longer time on that longer time plot. And when I actually did that, you can see that we were able to pretty closely approximate the experimental results with the simulation. both for the 2D measurements and for the linear absorption. Actually, something that I should show here, but we were actually also able to see that beating action as well. And there's nothing fancy in this simulation. It is just taking a two-level system and only putting in the vibrations that we observed experimentally, directly from our experimental results. So we were able basically to recover our signal just using that very simple way of introducing our vibrations. So the other thing that I had mentioned to you before was we wanted to know what was happening in terms of relaxation in that phonon sideband right before it gets emitted. And so, like I was saying, a 2DES is kind of like the mother of all third-order spectroscopies. From the 2D measurement, we can actually, if we integrate over our absorption axis here, we can get something which is called transient grading. Transient grading is basically a pump probe measurement, like I explained before. You're just looking at population dynamics. But in transient grading, so it's a third-order spectroscopy and pump probe. You have two interactions from your pump, one interaction from your probe. That's the third order. In a transient grading measurement, your pump interactions are split spatially. They arrive temporally at the same time, but they're split spatially. So you're getting exactly the same kind of information. You're looking at population relaxation. So when we did that for the system, we can obviously still see the vibrations. They're not as clear. It's not as easy to see when you're actually looking at the coherence aspect of it as well. So this is just to point out, we can see this is emission from our phonon sideband and from our zero phonon line here. So basically what we did, like I said, is we took all of our 2D plots, integrated over our emission axis. We get a 1D plot that's just frequency dispersed along our emission axis here. And we plot those all together. And so when we do this and we look at relaxation in our transient grading, so again, population dynamics only, we were able to see relaxation in that phonon sideband, our radiationless relaxation within that phonon sideband. And when we did that, we got a time scale of around 4 picoseconds. Now, this was actually, so there had been predictions in the literature saying that this should be about 10 picoseconds. But before I did these measurements, I thought it would actually be closer to a picosecond or so based on the density of states. Very high density of states. Should be able to relax faster. And so we got something which was actually around 4 picoseconds, which is really kind of slow when you think about where the density of states is and how this relaxation is happening. And so this actually fits back into what we observed with our vibrations. We have a number of vibrational modes which are very strongly coupled to the center. And so basically that acts as a way of thinning out our density of states. You have these modes which are more strongly coupled, and it basically reduces our apparent density of states to the excitation. So just to summarize this section of the talk, basically, we were able to do these 2D measurements that showed us a lot about the vibrational, ultrafast vibrational, and electronic dynamics of the system. We were able to show that there was picosecond relaxation in the phonon sideband. We were also able to identify a number of very strongly coupled local modes, vibrational modes that are local to the defect, and then able to simulate that data just using input from our experimental results. So I've showed you something which is pretty complicated that you can learn about using 2D electronic spectroscopy. However, we can still learn a lot about seemingly simple systems. So even small molecules in solution. As I said before, this measurement was also initially envisioned to be able to look at broadening as well. And we see some very strange things when we actually go and we look at light harvesting pigments, which are just small molecules that you can put into solution. So photosynthesis is one of the primary motive forces on Earth. It creates more than 100 billion tons of biomass per year, which is approximately equivalent to 2 times the Great Pyramid of Giza every hour. It's absolutely massive. So when you think of photosynthesis, you often think of, this picture of an old growth forest. This is actually Lighthouse Park outside of Vancouver. But believe it or not, more than 50%, well, actually just under 50% of the biomass production happens in the ocean. So you have photosynthesis happening in pretty much every environment on Earth, even at deep sea vents where no light from the sun gets down to. But what those guys are doing down there is they're absorbing infrared light from the vents. So there is photosynthesis happening almost absolutely everywhere there's life, one form or another. So, like I was saying, there's this huge diversity of different environmental niches. And in association with that, perhaps, there's a huge variety of different protein configurations that span the visible spectrum, the solar spectrum. So everything from these beautiful trifold forms from dianoflagellates. The short form for this is PCP, so please don't Google that. I made that mistake before. If you do, use the full form of the name, which is peridine and chlorophyll protein. Yeah. There's phycoerythrins, which come from cryptophytes, which are very, very old forms of photosynthetic systems. There's also LHC2 if you look outside. If you look at higher plants, pretty much everything that you're seeing is chlorophyll bound in these antennas. These are the antenna systems of higher plants. There's also a little complex here, which is between this is the antenna and the reaction center, where the process of storing light energy as chemical energy begins, from green sulfur bacteria. And this little guy nestled in between them is called the Fenner-Matthews-Olsen complex. It's basically a little wire that takes energy from the antenna to the reaction center. You may have heard of it before because it's a quintessential model system for photosynthetic aggregates. And it was actually the first system that was used to show that there are likely quantum mechanical effects happening in photosynthesis. And then we have the beautiful antenna systems of bacterial photosynthetic systems, the beautiful double ring systems. So you'd think there's a huge amount of diversity here. There's a huge amount of diversity in the protein conformation. If you go in and you look at what is actually absorbing the light, the chromophores, there is not really that much diversity. You have carotenoids, and carotenoids often perform a dual function. They can be protective, they can be light harvesting. They also exist simply as pigments. So for instance, when you're looking at a carrot, you're seeing beta-carotene, which is a carotenoid. When you're looking at a tomato, you're seeing lycopene. And we have the chlorophylls and bacteria chlorophylls, which are based around this chlorin ring. They're actually fairly similar to each other chemically, even though the bacteria chlorophyll absorbs around 800 and chlorophyll absorbs around 680. There's another kind of chromophore, which is in the phycoerythrins, which is called a bilin. And a bilin is actually a close relative of the chlorin. So there's not really as much diversity when we're talking about the pigments. That's kind of interesting. So why would nature preserve these pigments? Why would you use them over and over again? There's actually been a lot of work recently done on the synthetic biology side to try to make new molecules that mimic these photosynthetic molecules, so that you can actually build your own individual complexes for light harvesting solar cell type applications. And I was lucky enough to get one of these from a collaborator of ours. And if you compare, this is basically an analog of bacteria chlorophyll A. And if you compare it to naturally occurring bacteria chlorophyll A, you'll see that the linear spectroscopy is pretty close. So this is the absorption and the fluorescence for both of these. And so this is both taken at room temperature. If we then take this system and we actually cool it down to 4.5 Kelvin, we don't actually see much of a line shape change, which is kind of surprising. You'd actually expect to see it shrink down more as you freeze out the individual vibrational modes that are giving you the broadening. So we already knew there was something a little bit strange going on with bacteria chlorophylls. So when we did a 2D measurement on this, again, let me remind you, this is a small molecule in solution, not unlike the dye that I showed you before, at room temperature. So you see the line shape changes a little bit, but if we look at the diagonal elongation, so how much our peak is elongated along the diagonal there, this is at time 0, so right when you first have the excitation, and this is at more than 3 picoseconds at room temperature. So remember what's happening. You're having all this diffusive action going around. It should be sampling all the different parts of phase space. We don't really see much of a change. And so I was so surprised when I saw this. Sorry, the colors are reversed on this, but I actually made a video of it. This only goes out to about a picosecond, but you'll see there's very little change in the line shape. This was really shocking. So we thought, okay, well, maybe there's something weird going on with bacteria chlorophyll, this analog. Maybe it's not actually like bacteria chlorophyll. And so just to make sure we weren't doing anything funny in the experiment, I did a control, again with a dye. And as expected, here's our dye, our laser dye, and methanol. We start at time 0. We have this peak, which is elongated along the diagonal. We have an ellipticity of 0.57, very elongated. And then after only 200 femtoseconds, we're basically almost back to 1 here, very round. So we thought, well, maybe this is just something weird that's happening with our analog. Maybe this isn't something that actually happens in nature. Maybe bacteria chlorophyll isn't like that. Maybe there's something else weird going on. But when we actually measured bacteria chlorophyll A and ethanol, this peak over on this side here is an excited state absorption. But you can see at time 0, so at the first step along our excited state lifetime, very elliptical, 0.55, very elongated. 200 femtoseconds. So I'll remind you that this is the point at which we had completely collapsed down to something which was very round, had an ellipticity of nearly 1 for the dye. We still have 0.71. When we get to 2 picoseconds, we're still elongated along the diagonal. When we get to 100 picoseconds, we are back basically to 1. It's not ever going to go right back to 1 because we have this excited state absorption here. But you can see if we actually plot the ellipticity relative to our time along our excited state lifetime, you can see that it actually takes picoseconds to relax back. That is extremely strange for a small molecule in solution. Extremely strange. So we thought about it a little bit more. And actually, if you go and you look at the Wong-Rees factors, so these are the displacements associated with the vibration, and you look at what's happening in terms of bacteria chlorophyll A, so those are the red lines here, as opposed to a laser dye, which has a strong coupling, you'll see that you have a large number of very weakly coupled vibrational states. We thought about it a little bit more, and actually this makes a lot of sense. So you want to be able to have a large number of vibrations, something which is elongated for a fairly long time, because what this basically means is that you're maximizing your overlap between your individual bacteria chlorophyll pigments. If you're maximizing basically the energy span over which you can absorb, basically by having all of these vibrational modes that are weakly coupled but can accept energy spread out, you're basically going to be able to maximize that overlap. And in these systems, you always want to maximize the overlap because it basically comes down to an issue of time scales. You're competing against relaxation through fluorescence. You're competing against other pathways that, for instance, can form singlet oxygen and rip apart your delicate protein structure. You always are trying to move that energy as quickly as you possibly can down to the reaction center where you can actually start storing it as energy and you don't lose basically all that work. So in this case, basically, the presence of all of these weakly coupled vibrational modes, which actually also makes sense if you think about it chemically, because you've got a very rigid ring structure, maximizes the energy overlap between individual bacteria chlorophyll pigments. And then also by tuning the polar environment of the protein, you can maximize the individual overlap pairwise so that you can direct the energy flow through the system. So in retrospect, it's not terribly surprising that they would be elongated like this for so long. There are just not very many molecules, I think, that do that. And so that's perhaps one of the reasons why these kinds of molecules have been preserved through millions and millions of years. Okay. So I've talked about single molecules now in terms of photosynthetic systems. But what we're really interested in is understanding what happens in pigment protein complexes. And these are some of the larger complexes, the parts of the antenna, et cetera. And in those, basically what you have is a number of these pigment molecules that are very, very closely packed together and held into place with relative orientations, right, because that's going to affect how the energy moves between individual pigments, held into place in relative orientations in these protein matrices. This is the Fenner-Matthews-Olsen complex, which I mentioned before, which we're going to use as a model system here. And I'm actually going to move away from 2D now and explain a new experiment that involves this kind of a system here. In nature, it's actually a threefold system, but we generally look at it in terms of a single system here. It does have the protein in there, but we're only going to be exciting the bacteria chlorophylls. So really the holy grail of trying to do this type of spectroscopy on photosynthetic systems is to understand the connections between time, energy, and space. So we want to know when the energy is, basically how long it takes for the energy to move, where the energy is going, and where it's going energetically as well. So where it's going in space, where it's going in energy, where it's going in time. This can actually be a very, very complicated problem, especially when you have strongly coupled electronic systems. And basically the goal of these photosynthetic systems is to be strongly electronically coupled, because that maximizes the speed of energy transfer, that maximizes your coupling. So a way to think about this is, imagine that you have a dimer system. If these two parts of your system here, they're not interacting at all, you have no coupling, energy levels don't change. When you bring these two together, let's say you have a bonding interaction, you basically remap to a new set of energy levels. You do that when you're talking about a strongly coupled exciton system as well. You no longer think of the individual identity of the chromophores. So it's not as if you'd be absorbing into this chromophore here or this chromophore here. You're absorbing into energy states that are characteristic of all of the pigments together. So you're remapping it into a new set of energy levels that are exciton energy levels. So when you actually do that, you can then put multiple excitations into the system, right? You could think about exciting each of the pigments individually, but you're actually exciting individual exciton levels. When you do those excitations talk to each other. They're not independent. And part of the reason they're not independent is because they often have spatial overlap with each other. Oops, let's go back. They often have spatial overlap with each other. So they are actually talking and interacting. And because they're talking to each other and interacting with each other, we've actually come up with a new kind of measurement to look at them. I'm going to go through this quickly, and then I'll explain a little bit more, because it's a little bit of a complicated concept. So basically, in this measurement, we use a very similar setup to what we had before. But what we do is we remove our local oscillator, and we drop in filters. So basically what we're doing is we're separating our excitation from our emission. If you had no electronic coupling and you did this, you would see no signal, because you're basically you're not looking at any. So you're completely your detection wavelength range is completely separated from your excitation. Because the excitons talk to each other, because they overlap and they talk to each other, you actually get a frequency generation type thing, where you're seeing new frequencies appear at different wavelengths. And so that's what we're looking at here, because we've isolated our initial absorption from our emission. And when you do that, so again, this is right here is the linear absorption of FMO. This is our laser pulse with a very sharp cutoff filter applied to it. We have another very sharp cutoff filter at 810 for our detection. And what we see there is we see a third order signal. So it depends on all three beams completely. This over here is fluorescence, and as you would expect, it scales. It's basically additive with the three beams, so it's a linear process. So basically what we're interested in is this peak here. This is a new frequency that's being generated based on the electronic coupling between the excitons in the system. Now, there are a lot of these very strongly coupled electronic systems, both in nature and that can be made synthetically, etc. And even the reason for trying to come up with a new experiment here to study these has to do with the fact that a lot of these very strongly coupled electronic systems have the energy levels really close to each other. And even if you do a cutting-edge 2D electronic measurement, all you basically see is a blob. So this is a way of trying to decouple our electronic time and spatial contributions. So the reason that this works in a strongly coupled electronic system is because let's imagine that we have this sort of cartoon absorption spectrum here. We're initially exciting just in this tiny window here. And let's say that we've got an exciton with this spatial distribution. We're only exciting that guy. He's the only guy who sits at that energy. We're then detecting over here. If these two guys are coupled to each other, we'll see a signal here. So these two guys here are coupled through this pigment right there. We have overlap between them. Because we have overlap between them spatially, they talk to each other electronically. And we're following this using a time-resolved measurement, which gives our time component as well. if, let's say we had the other situation, let's say we had an exciton that spatially looked like this guy right here, and then at our detection window we had an exciton that looked like that. There's no overlap between them spatially. We would see no signal. So it's basically a case of, is there signal, is there not signal? And then what you can do is by systematically scanning through your absorption spectrum, you can actually pick out different contributions to the signal, and you can begin to map out your exciton structure, even if you're incredibly spectrally congested. All that you need to have for this to work is narrow enough filters and strong electronic coupling. Now, when I say narrow enough filters, they can't be super narrow, because you're still doing this as a time-resolved measurement. Through the visible, though, that requirement is not so onerous. You can have a pulse that's 100 femtoseconds with a spectral width of between 3 and 10 nanometers through the visible. And usually that's sufficient for most of the absorption spectra that we're looking at. So we did this on a test system initially. We did it on FMO, and really just in the one spectral range to show that it's possible. I'm planning on extending this and doing this on a number of systems, including the reaction center of photosystem 2, which is actually the site of oxidative photosynthesis, about which almost nothing is known currently because it's so spectrally congested. So when we did this experiment, again, we were able to frequency generate a new area, third order signal, 3-beam dependent. So if we actually map out, the reason for initially doing this on FMO is because a lot's already known about it. You don't actually have to have all of this initial knowledge in order for this experiment to work, but it's good to test that initially on a model system about which you know quite a bit. So this was our initial excitation band here. So we're initially exciting primarily what's labeled as exciton 6 and exciton 7. Our detection band was over here, so primarily exciton 1 and exciton 2. We were able to see signal. We know that those guys then talk to each other. And this actually helped us resolve a major question that we had in terms of energy flow through FMO. It wasn't really clear, before we did this experiment, why the transfer between excitons 4, 5, and 6 to exciton 2, so this is a relaxation, was very, very fast, while it was very slow to exciton 1. And if you look at the spatial extent of these excitons here, you see that there's overlap with exciton 2, primarily over this pigment here, as well as on this pigment and that pigment there. But with exciton 1, there's almost no overlap, because it would primarily have to be through a density over here. So that explains basically how we were able to get very fast energy transfer from these excitons to this one. And so from this experiment, if you go through systematically, you can disentangle the spatial extent of the excitons with the energetic extent of the excitons, including the time resolution, so how fast things are actually moving. So just to summarize very quickly, I told you a little bit about the recent measurements that we've done looking at the vibrational spectrum of nitrogen vacancy centers. We were able to see that there were a number of distinct, very strongly coupled local modes. We're also able to look at some of the anomalous behavior in photosynthetic pigments. And I showed you the first steps towards a new measurement that sort of balances on the limit between time and frequency resolved in order to be able to separate out interactions in strongly electronically coupled systems. So I just want to say thank you to you guys for your attention. Also thank you to my postdoctoral supervisor, to another postdoc in the Fleming group, Dr. Tom Oliver, who assisted me in the diamond measurements, and our collaborators, the Lindsay group for the bacteria chlorin and the Budker group in physics at Berkeley for collaborating on the diamonds. So, thank you very much.